Welcome to This Explainer. Today, we're diving into the ultimate Goldilocks mystery, the grand cosmic balancing act that makes our home planet so uniquely suited for life. It's a puzzle of literally unimaginable scale, and the answers? Well, they're hiding deep within the rocks beneath our feet and the stars above.
So let's just jump right in and ask the big question. Why does Earth teem with all this vibrant life, while our closest celestial neighbors are so, well, dead? You've got Venus, which is this toxic, boiling hothouse, and then Mars, a freezing, barren desert. What exactly went right for us?
To figure this out, we've got a clear roadmap. 1. Forged in the solar nebula. 2. Earth's dynamic layered interior. 3. The magnetic invisible shield. And 4. The carbonate silicate thermostat.
All right, Section 1, Forged in the Solar Nebula. Let's trace this all the way back to our origins.
This timeline right here really captures our chaotic beginnings. Going way back to 4.567 billion years ago, a massive gas cloud called the solar nebula contracts and collapses. Fast forward a bit to around 4.52 billion years ago, and our proto-Earth is quickly gobbling up highly oxidized materials, basically setting the stage for our rocks and water. But here's the crazy part. Shortly after that, a Mars-sized protoplanet named Theia literally smashes into us. This giant impact vaporized tons of material which eventually clumped together to form our moon.
Now, this brings us to what scientists call the isotopic crisis. Think of isotopes kind of like a planetary fingerprint. Meteorites from Mars or the asteroid belt, they have totally distinct signatures. But the Earth and the Moon, they share essentially the exact same chemical batch for elements like oxygen and tungsten. I mean, they are nearly identical. That tells us there was incredibly vigorous, complete mixing of material during that catastrophic Theia impact.
Section 2, Earth's dynamic layered interior. Since we can't exactly drill to the center of the Earth, scientists use seismic waves from earthquakes like a giant planetary ultrasound, and what they see are these distinct layers separated by sharp boundaries. We've got the solid crust on top, ending at the MOHO boundary. Beneath that is the thick, plastic-like solid mantle, ending at the Gutenberg boundary. Then, going deeper, you hit the liquid outer core at the Lima boundary, which wraps around the completely solid inner core.
But here's the thing, this layered structure isn't just sitting there. It's dynamic. That churning mantle drives plate tectonics, pulling the heavy, cooling oceanic crust down into the deep interior. This process carves out massive features like the Marianas Trench, dipping an absolutely mind-blowing 11 kilometers deep into the Earth.
And all of this movement creates what's essentially a massive geological conveyor belt. Hot magma rises at mid-ocean ridges, spreads out, and creates brand new oceanic crust. This crust acts like a literal conveyor, moving outward until it ages, gets denser, and eventually subducts right back down into the mantle to be recycled.
So what's powering this whole system? The inner core. Made mostly of iron and nickel, this center point is under so much immense pressure that it stays completely solid, even though it's burning at roughly 6,000 degrees Celsius. Just to put that into perspective, that is about as hot as the surface of the sun, right there in the middle of our planet.
All right, moving on to Section 3, the magnetic invisible shield.
The absolute key to our survival here is the geodynamo. Picture the molten outer core like a pot of boiling water on a stove. The swirling convective forces in this fluid, electrically conductive liquid metal, generate massive electrical currents, and those currents project a powerful global magnetic field way out into space.
When you compare Earth to Mars, you really see how vital this shield is. Here on Earth, that roiling liquid outer core sustains the geodynamo, giving us a robust magnetosphere that literally deflects harmful solar winds and cosmic rays, keeping our thick, life-sustaining atmosphere totally safe. Mars, on the other hand, well, its core cooled down and stopped convecting billions of years ago. It lost its global magnetic field, leaving only localized anomalies. Without that shield, the solar wind just violently stripped its atmosphere away.
And then there's Venus. It's almost the exact same size as Earth, but it suffers from a runaway greenhouse effect. Why? Because it lacks plate tectonics, meaning it can't cool its mantle efficiently, which stalls out any core convection. So, no global magnetic field. It's a stark warning of what happens when a planet's internal engine just stops.
Which brings us to our final piece of the puzzle. Section 4, the carbonate silicate thermostat.
Our atmosphere is this incredibly delicate balance. As you can see, it's about 78% nitrogen and 21% oxygen. but it's actually the tiny 1% of argon and trace gases, specifically carbon dioxide, that acts as a planetary blanket, keeping Earth warm enough for life through the greenhouse effect.
And this perfectly tees up the carbonate-silicate cycle, an elegant four-step continuous loop. Step 1. CO2 dissolves in rainwater to form weak carbonic acid. Step 2. This acid weathers continental silicate rocks, washing the ions right down into the sea. Step 3. Marine organisms use those ions to build calcium carbonate shells. Finally, Step 4. When those organisms die, the sea floor subducts, and volcanoes outgas that CO2 right back into the atmosphere.
This whole process acts as Earth's built-in weathering thermostat. It's a genius negative feedback loop. When the Earth cools down, weathering slows down. That means less CO2 is scrubbed from the air, allowing volcanic CO2 to accumulate and eventually warm the planet right back up.
This thermostat is seriously powerful. I mean, volcanic CO2 outgassing is what helped Earth escape those ancient snowball Earth glaciations. Plus, massive continental features drastically affect global weather. Take the Himalayan uplift. It exposed so much rock that it increased rock weathering and actually caused global cooling. The system is so responsive that if you literally moved the modern Earth further out in its orbit, cooling would slow the weathering down, and CO2 levels would just adaptively rise to keep us temperate. How amazing is that?
As geoscientist James F. Casting puts it, Earth's climate is buffered over long timescales by a negative feedback between atmospheric CO2 level and surface temperature. The big takeaway here? Habitability isn't just about your orbital distance from a star. It's an interconnected, dynamic system stretching from a molten core all the way to our atmospheric chemistry.
So, are there other Goldilocks planets out there waiting to be found by future telescopic missions like HABEX and LUVOIR? To find them, we really have to deeply understand our own home first. That's why cutting-edge missions like NISAR and Trishna are so important right now. They're monitoring Earth's shifting crust and temperatures in unprecedented detail. By studying our own delicate balance, we might just figure out exactly where to look for a second Earth hiding in the galaxy. Thanks for joining me on this explainer, and keep exploring.